Alright, so our next unit is all going to be about triangles. Now, up until this point, basically in geometry and trig, everything you've ever worked with was a right triangle. So you probably don't even know this word. But the word that I'm about to tell you about is an oblique triangle. So an oblique triangle is basically any triangle that's not a right triangle. So it can be acute or it can be obtuse. It's just not right. So this is a name that encompasses both acute and obtuse triangles. It's called oblique. So we're going to be talking all about oblique triangles and how do you find missing sides inside of an oblique triangle? How do you, okay, how do you find missing angles in an oblique triangle? How do you find the area? Is that possible? Up until this point, you may have thought it was impossible to find the area of a triangle that's not right, but in fact you can. So that's what this unit's all going to be about. So a couple things about an oblique triangle. Whenever we're talking about an oblique triangle, it's difficult to talk about the sides because there is no hypotenuse. So typically we label our sides A, B, and C, our angles, A, B, and C, with capital letters. And then the side lengths, since we don't have special names for them, we just call them by the lowercase version of their corresponding angle. So for example, angle A corresponds with side A, which is opposite it. And then side B will be across from angle B. And lastly, side C will be across from angle C. And so these are called corresponding sides and angles. So just a little bit of background before we start doing problems so you know where all these letters are coming from. Lowercase means you're referring to a side. Uppercase means you're referring to an angle. So you should go ahead and cut off the top portion of your foldable if you haven't done that already so that it looks like this. And we're actually not going to jump right into working out problems. What I want to start with is proving the law of sines to you. So I think it's important to know how these formulas are created. The ones that you're able to comprehend. There's some proofs that are just, it's silly to know, but this is one that you guys can actually understand. So first, let's read the law of sines. If A, B, and C are the measures of the angles of a triangle, notice they're capital, and A, B, and C are the lengths of the sides opposite those angles, then, and you have this triple proportion here. Now the thing about this formula is all it's saying is you don't have to have all three whenever you're solving a problem. A proportion is a fraction equal to a fraction. So say you have three of these variables and one missing, well, you can solve that proportion. Or you could do these two together, or these two together. All right, so don't be confused by the fact that you have three fractions that equal to each other. That's just to condense the law of sines into one statement. And that'll all come together a little bit more when you start to see some problems worked out. But first, I want to prove this to you. So go ahead and in your ISN, we're going to put this on page 75. And just ignore that mine says solve with factoring because I wrote that on there a while back and it was wrong. So this is actually skill 31. Alright, so we're going to prove the law of sines. And I'm going to put that really big over here. Prove the law of sines. And we'll be putting our foldable on the other page. Alright, so proving the law of sine. Well, in order to prove it, we have to start out, because what we want to end with are these angles and side lengths. So we need to start out with a triangle. We actually need to start out with an oblique triangle. So I'm just going to draw one here. And we're going to label the angles A, B, and C. And the sides correspond to that. So we have A, B, and C. Now at this point, to help us with our proof, we're actually going to include the altitude of this triangle. And altitude is just the distance from a vertex to a side, and it forms a right angle. And the altitude, since A is already taken, we're going to call it height. And we're going to call this little point where these two lines intersect D. So we've got side length C, then we've got point D. So all of that's just to set us up for our proof. So we want to try to prove that these proportions or these fractions are all equal to one another. Okay, so how do we do that? Well, the first thing that we're going to do is use our SOHCAHTOA, use some trigonometry that we know. And I'm going to ask, what is sine of angle B? All right, so what's sine of angle B? Well, hopefully you guys haven't forgotten that that is opposite over hypotenuse. So H over A. Now I'm going to ask, what's sine of A? Again, you've got opposite over hypotenuse, and since this creates a right triangle, the B is going to be our hypotenuse, so we have H over B. Now the reason why I did this was because, first of all, it's the law of sines, but also now we're going to have a common variable. With this proof, we have all this alphabet soup, but both of these equations have an H in them. So what I'm going to do is I'm actually going to solve for H. And so I'm going to multiply by A on both sides of this little equation, and I get A sine of B equals H. And in this equation, again, I'm going to solve for H, and I'm going to multiply by B on both sides, so I get B sine of angle A equals H. So now I've got two equations, both set equal to H. If they both equal H, that means they equal one another. So I can say that A sine of B equals B sine of A. So now I've got a formula. If I had three of these variables, I could plug, or I could solve it for another one. So this is actually the formula. But to make it easier to memorize and look at, they manipulated it a little bit. So they divided both sides by A, and they got sine of B equals B times sine of A over A. And then they have this B hanging out over here, and they divided by B on both sides. And their final formula was sine of angle B over side B equals sine of angle A over side A. Which is the exact same thing as we have here, just flipped over. So these are actually the same thing. We can rewrite it as B over sine of big B equals A over sine of A. And voila, we found one portion of the law of sines. And you can continue to do this proof three different ways, using the altitude here and using the altitude here. And you would get all three parts of this formula. And that's it. So it seems really crazy, but somebody tinkered with with the variables here until they figured out that, oh, there's this formula that exists, and then they manipulate it so that it looks a little bit easier, and you can memorize it a bit better. So now let's do some actual problems, and that was our proof. Make a little box at the end.